Let's take a look at number 34, and the formula you're going to want to use is on page 684 in the book, chapter 7. It's the sum of the terms of an infinite geometric sequence. So this sequence goes on forever. Now, it's only going to have a sum that it approaches if the ratio of how the terms are changing is less than 1. So let's first look at what the ratio is of how the terms are changing. So the first term is 15, the next one's negative 12. So 15 times what gives you negative 12? Because these terms are changing by the same ratio every time. So let's just solve this algebra by dividing both sides by 15, and we get that the ratio is negative 12 over 15. I guess we could reduce that, divide both by 3 here, and we get negative 4 over 5. So each term is negative 4/5 times the previous term. And you can check that if you took negative 12 and multiplied it by negative 4/5, you'd get negative 4 times 12 gives you positive 48, and then a 1 on bottom times 5 gives you 5. So this same ratio works to get to the next term, and you can just continue that way. If you multiplied this term by negative 4/5, you'd get that term, and so on. So we have the common ratio. We call that R, and it's negative 4/5. And here's the formula mentioned on page 684. You just take the very first term, which is 15, and then on the bottom, you're dividing by 1 minus that common ratio. So just use a little fractions here. I actually hadn't reduced this. Let's make this negative 4/5. Makes it a little easier. So 1 minus negative 4/5. Well, minus and negative is a plus, and if we're going to combine fractions, we need them both to have the same denominator. So I'm fixing these here. 1 becomes 5 over 5, and negative 4/5, instead of minus the negative, we're just adding 4/5. All right, and then when you do that, you just combine the tops. So we're going to have 5 plus 4 equals 9. So that's how we calculate this bottom here, just using our fraction rules here. Now 15 divided by 9/5, let's use fraction division. So 15 divided by 9/5 becomes 15 multiplied by 5 over 9. Remember, for division, we flip the fraction and change it to multiplication. So 15 times 5, let's make sure I get that right. 15 times 5 gives us 75. And this fraction is just a 1 on bottom, so 1 times 9 gives us 9. So we get 75 over 9, and then to reduce that, they're both divisible by 3, so divide them both by 3, and we get our final result. This is what the series would converge to if you keep adding terms on that follow this pattern of being negative 4/5 smaller than the previous term. So on 51, we're finding all rational zeros, and we're also factoring the function. And these two things go hand in hand. If we know a zero, then we know what the factor is. For example, if a 0 was 7, the graph crossed the x-axis at 7, one of the factors would be x minus 7. So where you want to probably start is the rational zeros theorem on page 328. It's in chapter 3, and basically it says that every zero we have, every rational zero, it's going to have a form here where if you write it as a fraction, the top number p is a factor of the constant. So in our polynomial, the constant's the number 3. The only factors of 3 are 1 and 3. Those are the only numbers that divide 3. So the top number has to be a 1 or a 3, and that could be negative as well, but a positive or a negative 1 or 3. And on page 328, it says the bottom number has to be a factor of the leading coefficient, which is 4. The only numbers that divide 4 are 1, 2, and 4. And again, positive or negative. So a 0 of this function has to look like one of these. It has to be one of these answers. There's no other choices but these 6. So the number 3, because you have 3 over 1, 3 over 2, or 3 over 4. And then your other options are 1 over 1, 1 over 2, and 1 over 4. Those are your only 6 options. So I suggest looking at the graph next. And if you look at the graph, it looks like 3 is definitely an answer, which was on our list, 3 over 1. And it also looks like we have an answer in between 0 and 1 here. It looks like positive 1/2. And it looks like here we have negative 1/2, which again, those are on our list. 1/2, 1 over 2, positive or negative. And how I would go about solving it is, since 3 is clearly 1, I would do synthetic division, or long polynomial division, where you take your polynomial and divide by x minus 3, because we know 3 is a 0. When you do that, you get a remainder of 0, which proves it's a factor. So you've proven that 3 is a 0, because this is a factor, remainder of 0. And then this is what you have left. So you get to this step, and this is a difference of 2 squares. So if you remember how to factor a difference of 2 squares, it's the square root of the first part minus the square root of the second part, and then the second term you do plus. And you can see if you solve these for x, you would have x equals positive 1/2 as the solution here, and x equals negative 1/2 as the solution here. But start off by making this list and then look at the graph, and it'll help you narrow down which of these are possibilities, and then you can do synthetic division to prove that they're actually factors, because when you divide, you should get a remainder of 0. For this 59 here, you're going to want to solve graphically. Plug these equations into your graphing calculator. Now, depending on what calculator you use, this one you can probably plug in straight away. This one you may have to solve for y, which means subtract x squared from both sides and then take the square root of both sides. And just to show what I mean there, it would look like this. You'd have to type it in once positive and type it in again with the negative, because when you take a square root of both sides, you get the positive and the negative answer. So when you type all those in, I did it on an online calculator here, you'll see that first one in red here, it's a circle. And then when you do the positive and the negative, you get this blue line. So it crosses twice. We're going to have 2 solutions, and that's what we're looking for. And so kind of use our answers here and look at it. You want to just trace then on your calculator and see where these 2 graphs intersect. So trying to make this a little more visible here. So I trace here, and negative 2.13 looks like an x value, and the y value is 1.57. So looks like D is the only possible solution. Now let's see if the other one checks out. 1.76 and 1.98. So yeah, it does check out. But you can kind of just look at signs here and throw out a few answers. For example, you knew this is negative, and because your calculator might not trace perfectly, but if you know it's close to negative 2.13, then you can probably throw out B, because it could be C, D, or A, because your calculator may not be perfect. But then it definitely has a positive y value. We're above the x-axis, so we can throw out A, and we can throw out C, because they both have negative y values. So this is the only point that's even in the vicinity of where these things are crossing. So we get D by process of elimination there. But your calculator may, if it's very precise, you may get these exact answers that mimic what the choices are. Otherwise, just look at the signs and think about where this point would be. Negative would be down here somewhere. Same with B, same with C. So there is no crossing at negative. It has to be D where it's negative positive. 60 is going to be very similar. Your calculator should be able to do that right away. In this one, you're just going to need to solve for y by taking the square root of both sides after you subtract x squared. That's still from 59. Sorry. Here's the graph. You'll get something that looks like this, and then just zoom in on those points. I can get them exactly here on this calculator where they cross. That's what we're looking for the solutions, is where those two graphs cross. And again, note that one's going to be positive, positive, because it's up here in the first quadrant, and the other one's going to be positive, negative. So if it was multiple choice, that could help you narrow it down. But zoom in as close as you can on your graphing calculator, use the trace feature, and then see where those cross. But for 65, you're really just going to want to evaluate this by plugging in the values for k. So k is 2, 3, 4, and 5. It goes up through from 2 to 5. So maybe I'll use Excel here. So first, you're going to want to plug a 2 in. So you're going to get -1 to the second, to the 2. Sorry, to the 2 plus 1. And then multiply that by 2 minus 2 squared. And you get 0 because 2 minus 2 is 0. So I'm just going to copy that. And let me actually make it a little easier to remember. So when we plugged in a 2, we got 0. What happens when we plug in a 3? I'm going to replace the k's with a 3. And I get 1. What happens when we plug in a 4? I'm going to replace the k's with a 4. And we get -4. And what happens when we plug in a 5? I replace the k's with a 5. And I get 9. And so you're just going to want to sum those up. So your sum here is 6 for k equals 2 to 5.